and black. So represented by VR, Vy and VB. So these are the three phase voltage. Now we derive relation between these two line voltage and phase voltage. So we have to go with one phasor diagram and then we can derive this equation. So from the given figure we know that we can take a vector summation. See in this figure, here voltage VRY is voltage between R to Y. So if I taking the vector summation in this branch, then it is a vector summation of VR and VY, or I can say that it is a vector summation of VR and VRN and VNY. So this relation is also represented by the vectors. So from the given figure, our vector relation is given by VRY equal to VRN plus VNY, as seen in the previous figure. Now I just convert this voltage into negative sign, so VRN. If I write down voltage YN, then its sign is change, because we have converted, first we measure voltage neutral to Y, now we measure voltage from Y to neutral, then it is a change. So sign is becomes negative, so VRN minus VY and as we know that the voltage between R and is also known as voltage between R, and similarly voltage between Y and is also known as voltage between Y. So now equation is modified. Vector summation VR is equal to, it is a VR minus VY. So let's see, in this equation we get the VRY is a vector summation of VR and VY, but it is a vector summation, so we have to say that it is a summation of VR and minus VY. Vector summation of VR and VY gives VRY. So vector summation gives VRY. So these all are the vector quantity. So vector quantities can also be represented by the phasor diagram, and we can derive the relation using the phasor diagram. So we go with the relation with the phasor diagram to get the answer. Similar quantities are representing in the PPT also. Okay, so we go with the previous. Now we representing that by the vector diagram. See, it is a vector VR, VY and VB at the 120 degree. Now the line voltage or VRY is given by a 30 degree VRY, or you can also say it is a line voltage VL. So this represented by the vector OA. Now if I am taking one perpendicular from this point, it is a 90 degree, is perpendicular, and this angle is 30 degree. This angle is 30 degree. You can see that this angle is 30 degree. So now this point is B and this point is C. So perpendicular is 90 degree. This triangle is become in that triangle OBC. So here we get one triangle OBC. Now for that triangle we write down the quantities, or we apply our Pythagoras theorem. Our quantity is write down here. The side OB is given by OB equal to cos 30 into OC. Now here OC is represented VR vector, and what is OB? The OB is half of the line voltage VR. OB is the half voltage of VR, so kept as it is. So value of cos 30 is root 3 by 2 into value of OC is vector quantity VR. So we get OB equal to root 3 by 2 VR, where VR is phase voltage. So OB equal to root 3 by 2 phase voltage. OB equal to root 3 by 2 phase voltage. And as we know that OB is a half of a OA. OB is a half of OA. So from this we get that, see from that, here line voltage or VRY is given by 2 times OB, 2 times OB. As we know that value of OB is root 3 by 2 VPH. So 2 into value of OB is root 3 by 2 VPH. 2 cancel, so we get line voltage equal to root 3 phase voltage. So it is a complete derivation of line voltage is equal to root 3 PH. Now similar relation we get for current in a star connection. For the current, IL equal to IPH. That means in a star connection voltage relation is given by VL equal to root 3 VPH. That means line voltage is equal to root 3 phase voltage, and in current line voltage are equal to phase voltage. So for the 8 mark we have to go for complete derivation, and with 2 figures and with the vector diagram we representing the relation VL equal to root 3 PH. Okay, thank you. Now okay, the next question, prove that in a pure inductive circuit current lags behind the applied voltage by 90 degree. Again 6 mark example. In that example we have to prove that for AC circuit, a pure inductive circuit, current is lagging behind the applied voltage by 90 degree. So again we go with some vector quantity and we have to go with some proof. So let's see the figure. See in the OHP, here we have taken pure inductor. An inductor is connected with AC supply. It is a pure inductor and voltage is applied is Vm sin omega t. Vm sin omega t. Here in pure inductive circuit there is no any voltage drop. So in pure inductor voltage drop of resistor is 0. So pure inductor has 0 resistance. Now for the second point, as per Faraday's law of electromagnetic induction, as per Faraday's law, previously we have discussed the Faraday's law. In that law we have discussed that when the current passing through the coil, when current I is passing through this coil, the flux is induced in the coil, and due to the flux some EMF is also induced. So as per the Faraday's law, EMF induced in the coil, EMF induced in coil. So induced EMF in the coil is given by E equal to L di by dt. Equation number 1. In the coil, induced EMF is given by E equal to L di by dt. Now, magnitude of this self-induced EMF is equal to the applied voltage, because in this pure inductor only coil is there is no any resistance, that means zero resistance. That means induced EMF is equal to the applied voltage. Here induced EMF is equal to applied voltage, and that is Vm sin omega t. So induced EMF E and Vm sin omega t both are equal, so we put Vm sin omega t in a place of E. So now equation 1 is modified. So equation 1 is E equal to L di by dt. Now in place of E I put Vm sin omega t equal to L di by dt. Now I am taking separate out di and dt, so L is gone here, so it becomes, taking this side, Vm by L sin omega t, again dt is this side, so here di is remaining. So Vm by L sin omega t dt equal to di. Now we take integration on the both sides. So taking integration on both sides, I write down I previously, so it becomes integration nothing, that means 1 di equal to integration Vm upon L sin omega t dt. Now from this side, in the integration part, 1 is integrated with respect to I, while in this side Vm and L are the constant, so only the omega t is integrated with respect to t. So let's see how the integration is done. Integration of 1 di, projector please. So integration of 1 with respect to di, it gives current I equal to Vm and L constant quantity, so we are taking outside, so integration of sin omega t dt. Now Vm upon L, integration of sin with respect to t is minus cos omega t, and omega t again is differentiate, then we get omega in denominator, so cos omega t upon omega. Now we take omega outside, then we get Vm upon omega L, and taking minus outside, so cos omega t. Now from the basic mathematical formula, we trigonometric formula, we converted our cos omega t into sin term. So how it can possible? We get sin pi by omega t minus pi by 2, sin omega t minus pi by 2. Now I giving this minus side inside to the bracket. When this minus sign goes inside the bracket, these two quantities are changed, so we get Vm upon omega L, sin quantities are interchanged, so we get omega t minus pi by 2. In this step we have already applied, so it become omega t minus pi by 2. So this equation is compared with instantaneous quantity. Now we know that the value of instantaneous current is I equal to Im sin omega t plus 5. So instantaneous quantity I is Im sin omega t plus 5. So we compare our previous equation, I equal to Vm by omega L sin omega t minus pi by 2. So by comparing these two equations, what we get, then that equation we get current Im equal to Vm by L. So we get maximum current is Vm by omega L, and Vm by omega L is known as XL. Okay, and now again comparing for the angle, we get the power factor angle phi equal to minus pi by 2. Now this is important because the phase difference or angle is minus pi by 2, which represent that current is lags behind the voltage by minus pi by 2. So it represents that the current always lags voltage by 90 degree, means pi by 2. Voltage lags current by 90 degree. Let's see in the figure how it represented. See in the PPT here, blue waveforms are represented voltage, and with a 90 degree phase difference current is representing. That means in equation Im sin omega t minus pi by 2, current always lags behind the voltage. So if I am taking voltage as a reference vector, then current is 90 degree lags, and if current is taken, then voltage is again at